We've heard it said time and time and time again.
The farther away a boat is, the more the bottom of the boat will disappear, and you'll basically just see the mast of the boat.
If you send a ship straight to the horizon, eventually it begins to disappear until it's no longer visible beyond your horizon.
Right.
And you should ask yourself, what kind of surface would produce that result?
That wouldn't happen if the Earth were flat. You would simply see the boat getting smaller and smaller and smaller as it went farther away, but you'd be able to see the whole thing with the same proportions.
The world is curved. I mean, it's a big curve, but it's curved.
Sorry to burst your bubble, but boats appearing to sink on the horizon don't prove that the Earth is curved. There is a key feature that each of these people have forgotten to factor in or have utterly ignored, and that is the atmosphere, which has the ability to refract the light that passes through it. As we know, we live in an atmospheric gradient. The atmosphere is less dense at higher elevations than it is at lower elevations. Since the atmosphere is denser at lower elevations, that's why the horizon appears white. It is because there is more atmosphere down there to reflect that light back to you, as compared to up above, where it becomes dark blue, where there is less atmosphere to reflect that light back to you. So yes, we live in an observable atmospheric gradient. Now take Snell's law into consideration here.
Let's imagine that I had a car. So let me draw a car. So we're looking at the top of the car. So this is the passenger compartment. It has 4 wheels on the car. I'm looking at it from above. And let's say it's traveling on a road. It's traveling on a road. On a road, the tires can get good traction. The car can move pretty efficiently, and it's about to reach an interface. It's about to reach an interface where the road ends, and it will have to travel. It will have to travel on mud. It will have to travel on mud. Now, on mud, obviously, a tire's traction will not be as good. The car will not be able to travel as fast. So what's going to happen? Assuming that the steering wheel isn't telling it to turn or anything, the car would just go straight in this direction. But what happens right when which wheels are going to reach the mud first? Well, this wheel right here is going to reach the mud first. So what's going to happen? There's going to be some point in time where the car is right over here, where these wheels are still on the road, this wheel is in the mud, and that wheel is about to reach the mud. Now in this situation, what would the car do? What would the car do? And assuming that, you know, the engine is revving and the wheels are turning at the exact same speed through at this, you know, the entire point of this, the entire time of the simulation. Well, all of a sudden, as soon as this wheel hits the medium, it's going to slow down. This is going to slow down, but these guys are still on the road, so they're still going to be faster. So the right side of the car is going to move faster than the left side of the car. So what's that going to happen? I mean, this is you see this all the time. If the right side of you is moving faster than the left side of you, you're going to turn, and that's exactly what's going to happen to the car. The car is going to turn. It's going to turn in that direction. And so once it gets to the medium, it'll now travel. It'll now turn from the point of view from the car, turning to the right, but it'll now travel in this direction. It will be turned when it gets to that interface. Now, obviously, light doesn't have wheels and it doesn't deal with mud, but it's the same general idea. When I'm traveling from a faster medium to a slower medium, you can kind of imagine the wheels on that light on this side of it, closer to the vertical, hit the medium first, slow down, so the light turns to the right.
So according to Snell's law, when light travels through a medium of varying densities at an angle, it bends in the direction of the greater density. With that being the case, the sunlight that travels through the atmosphere is going to get bent downward toward the greater density. Alright, so how would that affect our view of a sailboat out on the horizon? I've got an experiment I want to show you to demonstrate exactly what we would see. Here I have 2 fish tanks, and I'm taking a picture looking through both fish tanks. Now this is our control image, just seeing the boat through plain water. Now here I'm shining a laser through the 2 fish tanks so you can see the light going straight. Next I added a bunch of sugar to the water to create a gradient. Now I'm going to shine a laser through the 2 fish tanks, and you can watch that light bend downward toward the greater density. I also added some washcloths to the bottom of the tanks to help absorb the light and keep it from bouncing back up. Now let me show you what the boat looks like when the light gets refracted downward. Here our camera is in the exact same location as our control image, and now we are looking through a density gradient. Now here's a side-by-side to compare with our control image. With this, the first thing I want to point out is how much higher the bottom of the fish tank appears in our refracted image than it does in our control image. Next, I want to point out these yellow lines, which are exactly the same length. Please notice how the top of our refracted boat appears closer to the bottom of the fish tank in our refracted image than our control image. Here's a close-up for better comparison. And as you can see, the top of our refracted boat appears much lower than the top of our control image. This creates the effect that makes the boat appear to sink out on the horizon. So boats appearing to sink on the horizon don't prove that the Earth is curved. They only prove that we live within an atmospheric gradient. Further proof of this can be found when looking at faraway objects during different times of the year.
On a normal day, say in the summer, you can see Chicago, but only a dozen or so of the tallest buildings.
Anything more than that, especially once you get over 10 or 12, something's happening because that's not usually there.
The views along the lake are always changing, along with the weather.
And during the wintertime, you can see a lot more because the atmosphere is a lot drier than it is in the summertime. This creates less refraction in the air, not more of it. We can talk more about that in another video. Thank you all for watching.